So this is the mean value theorem where you have a function that is continuous in a closed interval AB and differentiable on the open interval AB. Then we say that there is at least one point C where f prime of C is equal to the average rate of change, which is f of B minus f of A over B minus A. So that's the statement of mean value theorem. Now we're going to use that to answer this problem. So suppose f is differentiable, so some arbitrary function f that is differentiable, and you're given f of 1 is 2, and you're also given that the derivative at any point within that given interval, let's say, is less than or equal to 5 for all x. So we want to find what is the largest possible value for f of 4. So for something like that, you're going to set up this formula using what's given to you and just solve that inequality. So we're looking at f of 4 minus f of 1 over 4 minus 1. So the interval we're looking at, it's 1 to 4. That's the interval. And we want this to be less than or equal to the derivative, so that would be 5. And then just cross multiply and isolate. And I know f of 1 is given, so this right here is 2, so I can substitute that in there. This is f of 4 minus 2 over 1 minus 4, that's 3. Less than or equal to 5. And then we just keep on solving this. Multiply both sides by 3, you have f of 4 minus 2 is less than or equal to 15. And we add 2 to both sides. So f of 4 must be less than or equal to 17. So the largest value f of 4 can be is 17. It has to be less than 17. So that would answer this question. What is the largest possible value for f of 4? Equal to 17 or less. So let me know if this makes sense.
Okay, so just to recap, what you did there was identify what you were given, which is f of 1, and then you use the interval from 1 to 4 because f prime of x has to be less than or equal to 5. Is that where you got the 1,4 from?
Well, I got 1 from here. That's the first function value. And I got 4 from here. So my interval is 1 to 4.
All right.
And f of f prime less than or equal to 5, that's the condition on this guy right here.
Okay.
Okay. All right, so that's that. Let me know if anyone has any other questions on this. So know the statements and know how to use it. Just a quick, algebraic problems. And for the intermediate value theorem, there are plenty of them on the homework set. And there's also one on our second test or the first test. I don't remember right now, but go through that solution. I hope that will make sense. So let me go ahead and take the next problem. Okay, so for the domain, we know that it's continuous everywhere except for 2 and -2. You have vertical asymptotes. So let's draw that. So here's our xy plane. And vertical asymptotes are -2 and 2. So I'll draw them right here, indicating using dotted line. Now, another thing you also want to find is the horizontal asymptote. So for this problem, what's the horizontal asymptote?
1.
1, right? It's right here. You take the limit as x approaches plus and minus infinity. And we are going to draw that right up here. So first, if it's a rational function, show the asymptotes first. It gives you a nice grade on graphing it. Now, do we have any max or min?
We have our local max.
So we have
0.
right here, local max. So let's indicate that. So if you have a max or min, plot them first after the asymptotes. And now the sketch. So So we know the sketch is going to be either here
Mhm.
or down here. Now, do we have any x-intercept?
I don't think so.
No, right? The only x-intercept we have is 0, 0. So right here. X and y intercept, they're both 0, 0.
Mhm.
So that means the graph, you know automatically that it's not going to be down here because there is no x-intercept. And it's not going to be here because there's no other x-intercept than this one right here, 0, 0. So that means we know the graph is going to be up there. But now let's figure out how we're going to sketch that. And that's when our increasing, decreasing, and concavity comes in. So from negative infinity to negative 2, what's going on? So here, it's increasing, right?
Mhm.
And then here, it's concave up. So concave up and increasing, you have to shape it this way. This is increasing and it's concave up. So it's like a happy parabola if you were to continue on concave up. Now, in between, you know, you have to hit the maximum. So you're not going to hit the maximum this way. It wouldn't make sense.
Mhm.
You'll have to hit the maximum this way. So now let's look at the first derivative test and concavity. So that's between negative 2 and 2. That's right here. And right here. So you're always concave down, but from negative 2 to 0, you're increasing. So this is increasing and it's concave down. So concave down is a, you know, frowny parabola. So I'm going to increase, this is increasing, and I'm concaving down. When I hit the maximum, and then I'm still concave down, so I'll continue to concave down, and I'm decreasing. So this is decreasing and concave down. Now the last piece, we already said we know the graph is not going to be here because we didn't have any intercept. But now if you look at your derivative test from 3 to infinity, sorry, from 2 to infinity, it's right here. You're concave up and you're decreasing. So concave up, again, it's a happy parabola and you're decreasing. So it has to look like this. So smooth like that. That will be concave up and it's decreasing. So let me know if this makes sense.
Yeah.
So try maybe another one after we leave. And I did work out 2 more in my YouTube videos, so check those out. But first work it out on your own, so that way you can check your work with mine.
Someone asked, isn't it increasing? That last part.
The last part is decreasing. It's right here. 2 to infinity is decreasing. So this is decreasing because your tangent line has negative slope, but it's concave up.
Okay, he said he
Alright.
got it.
Okay. Yeah, thanks for helping me out with the chat. Appreciate it. All right, so anyone else have any other questions? So you have a circular plate. So we're talking about a circle is heated in an oven and its radius increases at a rate of 0.01 centimeter per minute. So this means that's the rate of the radius, right? So let's call it dr dt. It's increasing respect to time. That would be 0.01 centimeter per minute. Sorry, I ran out of space. At what rate is the plate's area increasing? So we're looking at the rate of the area. That's what we're looking for. When the radius, so that's r, is 50 centimeter. So here's a picture. And we want to know how fast is the radius increasing. Now, what's the area of a circle? You guys should know that.
Pi r squared.
Yeah. So we know that's pi r squared. Now start taking derivative respect to time. So we're going to differentiate this respect to time. So on the left side, you get your dA dt. On the right side, pi is a constant, keep it as it is. So you're only differentiating r square. So that'll be 2r, but you have to tag along dr dt because it's implicit. So you get 2 pi r dr dt. Once you do that, you just simply sub in what's been given to you since everything is given and the component you're solving for is already isolated. So it's already nice and clean. Plug everything in. This is 2 pi times r 0.01. Sorry, r is what? Sorry, I plugged in the rate. 50. There we go. So it shouldn't be like this, but of course, multiplication is commutative, so it doesn't really matter. And just multiply these out. What do you get? You get 100 pi times 0.01. Well, that's also 1 over 100, right? So they cancel out, it's just pi centimeter square per minute. Yeah, so that will be the rate for the area. Let me know if this makes sense.
Wait, Professor, I have a question.
Uh-huh.
Let's say you didn't know how to like convert, like, you know, like the decimals. Could you leave it as that? Would it be wrong? The 100.
You mean leave it right here?
Yeah.
Yeah, that's fine. I wouldn't mind. Since you guys don't
Oh.
have a calculator, it's okay. Just simplify as much as you can. So if you didn't know that this was 1 over 100, that's okay, but we could multiply those, right?
Right.
Yes. Mm-hmm.
Someone asked, will the formula for the area be given?
For which shape?
This one, area of a circle.
No, this one you're supposed to know. This one is not given. So usually what they give you on the final is the volume of a cylinder or a cone. Those two are given to you on the final. If they appear on the final, they'll give you those volume. But for rectangle, for circles, for cubes, those are formulas that you're supposed to know. So I would say just look at them once so that they stay in your mind for a while.
The next question, someone said,
Okay, so here you go. So we pull out the 4, right? And we realize it's a sine inverse, right? So this is 4, the integral of 1 over square root of 1 minus x squared from 0 to 1/2. We know this is sine inverse, so we get sine inverse of x, and we're going to take it from 0 to 1/2. So now let's plug in the upper limit and the lower limit of the integration. So we have sine inverse of 1/2 minus sine inverse of 0. Now this is your pre-calc knowledge. You should all know at this point what this is. What is sine inverse of 1/2?
Pi over 6.
Pi over 6. Good. You have to say it with confidence. Well, I forgot the 4 too, so I'm going to put it there. Sorry. I left the 4 behind. So this gives us 4 times pi over 6 minus what's sine inverse of 0?
0.
0. Good. So this goes away. So all of this simplifies to 4 pi over 6, which is 2 pi over 3. So that will be the answer to this problem. All right, cool. Any questions on this problem?
a quick question someone asked was, does U-substitution work with definite integrals too, or is it only with indefinite?
It's for both. So you can use U-substitution depending on what you're integrating. It could be either definite or indefinite.
Someone said, could you do?
So, but we know that our linear approximation is going to be L of x, which is equal to the function value at a plus the derivative at a times x minus a. Now I'm going to pick a to be 0 because I know 0 is close by this number right here, and I also know tangent of 0 is, okay? So let's find our f of a. So we're picking the function f of x to be tangent of x because you're approximating tangent of some number. So it makes sense to pick tangent to be your function. So now find its derivative. We know that's going to be secant squared of x. And now plug in a into tangent to find the y value. So if a is 0, f of a, which is the y value, that will be tangent of 0. And that's also 0. So my x and y value are both 0. Now let's find the derivative at a, which is 0. That will be secant square of 0. So secant is reciprocal of cosine. So this is 1 over cosine square of 0. And what's cosine of 0?
1.
1. So this is 1. So my slope is 1. And my points, x coordinate and y coordinate at 0, 0. So plug them into your approximation formula. So L of x, it's going to be, so this is 0 plus 1 times x minus a. A is 0. And we're going to use, why does this look so weird? Okay. We're approximating 0.01. So this would be 1 times 0.01, which is just 0.01. That's what I got. It looks weird. But yeah, that's what it is. So yeah. All right. So well, it's been more than 30 minutes. So any last minute question? I do have to go.
This is a dilemma here. There's 2 questions left.
Okay, so we'll answer both of them and then that will be it.
Someone asked, Professor, can you go over substitution with indefinite integrals real quick? I don't understand which part do we consider as U.
Okay, so we do a U-substitution. No, I did do some last time, but let's do a different one. So let's do well,
the question that I had was an indefinite integral U-substitution.
So
that was like my question.
Oh, so it's the same. Oh, so give me your problem.
So the indefinite integral of 3y times radical, and then this is everything underneath the radical, 7 minus 3y squared.
Like that?
dy.
No, is it definite or indefinite?
Indefinite.
Okay, so there is no limit. No, I think the other person wanted a definite integral, right?
And it said indefinite.
Indefinite. Okay, so we're good with this. So, well, let's see, right? So what are we going to select U to be? Now you have to be clever in this because whatever you select U to be, some version of the derivative has to appear in the integral. So what do you guys think?
7 minus 3y squared.
Yeah, right. So I'm going to pick that because if I select this to be U, then I can rewrite the integral as square root of U and some variation, right? So that's only just the inside of that radical will be our U. So let U to be 7 minus 3y squared. That means the derivative of U will be negative 6y dy. Now let's check what we have in the integral. So I know this is going to be U, but what about the rest? Well, I needed 3y dy to replace those factors from here. So how do I do that? How do I make this expression look like 3y dy?
You divide the negative 6y both sides.
So not negative 6y. We can do better than that. But negative 6y would work, but we can do better. So what if I divide by negative 2? Would you agree? You get the exact substitution,
Yeah.
right?
Oh, yeah, I
You see it? But if you divide by 6, negative 6, that's still fine. You just have to, you'll get the fraction at the end. So if you just do this, you get 3y dy. And that's exactly what I have right here. That's why I wanted to make exact substitution. But if you didn't see that immediately, that's okay. Just divide everything by 6, negative 6, and then take out the 3 from y from the integral. You'll still get the same answer. So now let's go ahead and sub in. So our integral in the u variable is the integral of a square root of u times, now 3y dy is replacing this. So that's negative 1/2. I'll pull it out, du. And now we're ready to integrate this using power rule of integration. So this is
Is it
a
a negative? Oh, sorry.
Yeah, I lost it, but good catch. Negative 1/2 integral of u to the 1/2 du. So I'm writing it as a power. Now we add 1 to the power, same power goes on the bottom. So this is negative 1/2 u to the, so a half plus a 1, that's 3/2, divided by 3/2, or I can reciprocate that. So that would be 2/3. And of course, plus c because it's indefinite. Now here's where the change will be when it's a definite integral. You don't write plus c, instead you'll take it from some upper limit to lower limit. Now let's clear things up. So our final answer is negative 1/3. U is plugged back in. This is u. So that would be 7 minus 3y squared to the power 3/2 plus c. So that would be our final answer. So those of you who had question on this, let me know if this makes sense.
Yes, and it cleared up a lot of my confusion. I think I can finally do these now.
Oh, good. Good. That's good. All right.
Why, somebody asked, why is it negative 1/3?
Because I cancel out these guys.
He said it was understood.
Okay, cool.
Since that was only one question and you said you could answer 2, someone else said, I have one more question, but has not posted the question.
All right, so let's take that as our last question. So I
you-
don't know who it was.
It was, I don't want to mispronounce the name, but I believe that person is listening. So comment the question, please.
Yes, it's one of the homework questions, but it's the limit as x approaches infinity. Ln times open parentheses x to the power of 1/x close parentheses.
Okay. All right, so well, let's take the limit, right? What do we get?
Infinity to 0.
Right, so this looks like it gives you the form infinity to the 0 power. So how do we approach these kind of limits?
Take the derivative. L'Hopital's rule.
Right, you're gonna use L'Hopital's rule, but first you have to rewrite it, right? So let's do it. So I'm gonna call this f of x. So let f of x be equal to ln of x to the power x. And now I take ln on both sides. So I have ln of f of x is equal to, now when you apply ln here, the exponents will come forward. So you'll have ln of x times 1/x. And 1/x, I can write it like this. So this is ln of x over x. So that's your function ln of f of x. Now we can start taking the limit. So let's bring it right here. So this is the limit as x approaches infinity of ln of x over x. Now what happens when you take the limit? So as x goes to infinity, what happens to ln?
Does it go
Infinity?
to 0? No.
Infinity. This is going to grow slowly, but it will still go to infinity, right? And on the bottom, you have x. So if you go to infinity, you'll still go to infinity. So you have this indeterminate quotient, which is infinity over infinity. Now you can use L'Hopital's rule. So now this is our favorite part, right? You just take derivative on top, derivative on the bottom. So limit as x approaches infinity, we're taking the derivative of the top, that's ln of x, and we're going to take the derivative on the bottom. Oh, sorry, I didn't mean to write that. I meant to write this. Right, L'Hopital's rule. Now, when you take the derivative here, this is going to be chain rule because it's ln composed with ln. So you'll have the limit as x approaches infinity of 1 over ln of x times the derivative of ln of x, that's 1 over x. All over, derivative of x is 1. And now let's take the limit, what happens? So you're taking the limit as x approaches infinity of 1 over ln of x times 1 over x.
Isn't it 0?
0.
Yeah, because the bottom goes to infinity very fast, right? So you have 1 over very large number, so that limit is 0. But that's not our final answer. Our final answer has to be, because that's the limit for this function. So we need to exponentiate.
So e to the 0?
Yeah. So we took the limit as x approaches infinity of ln of f of x. But because that wasn't our initial question, we applied ln. To undo that, you have to exponentiate. So we're going to write it this way. And that's going to be e to the limit we just found. That would be 1. So that will be the final answer. So be very careful and make sure to always rewrite, look back, double check your answer. Don't rush because you guys have 2 hours, 15 minutes, and that's a lot of time for, for the final. So take all of the time. All right, so I am gonna stop here. A quick question.
Has it been said how many questions the test is gonna have?
Usually 10, but with a bunch of parts. So just like the samples, yeah.
Miss, I sent you an email. Should I wait for an answer or should I just?
I'm gonna
you
get
now?
back to you. No, I'm gonna get back
Okay,
to you.
okay.
Yeah. Well, thank you everyone for coming. I will see you guys the day of the final and continue to study and take some nice walk and have fun and then study and have fun and study again. And reach out to me if you have any questions.